Good morning, everyone, or good afternoon for those of you who are joining us through different time zones. Welcome to ITRI's online forum, Enabling Future Smart Factories with Intelligent Robotics. Before we begin, you may notice that your screen may be cropped off. So take a minute to adjust your screen by right-clicking on your screen and choosing Adjust to Full Screen. Okay, so let's see today's agenda. So as can be seen on the screen today, today's agenda is comprised of 3 topics. Each session will be followed by a 10-minute Q&A. Please ask any questions using the chat function. Also during this time, the QR code for the survey form will be shown on the screen, and a link will also be provided in the chat room. For those who are unable to stay with us throughout the event, please let us know your feedback. We'll share today's presentation files upon receiving your feedback. So now let's take a minute to test the chat function by typing hi. Okay, great, thank you. So now let's get started. Let's welcome Dr. Bingxiang Yang, Deputy General Director of ITRI's MMSL, and Dr. Yuliang Zhong, International Affairs Officer and Representative of ITRI Europe Office for some opening remarks.
Esteemed participants and distinguished guests, a warm welcome to today's online forum. My name is Bingxiang Yang, Deputy General Director of Mechanical and Mechatronic System Research Laboratories, MMSL at Industrial Technology Research Institute, or ITRI in Taiwan. We are delighted to have you join us as we embark on an exciting journey into the world's intelligent robotics and its transformative impact on manufacturing. In this dynamic era of Industrial 4.0, the fusion of robotics and artificial intelligence has changed the way we conceptualize, design, and operate our factories. The rise of intelligent robotics has opened infinite possibilities, empowering industries to enhance productivity, efficiency, and safety like never before. Throughout this forum, we will share our experience working with international partners in Horizon Europe's Hard2 project, and our contributions toward achieving flexible manufacturing with advanced AI-enabled robots. We will see how auto AI annotation and domain randomization approaches bring about VR and digital twin technologies which make Meta Factory possible. Lastly, we will delve into the most ingenious advancements in autonomous mobile robots, or AMR technology, including industrial Mars and its target follower function, pick and place robust localization, as well as extended applications into cleaning and art. 3 researchers will share their insights, experience, and vision in their areas of expertise. I welcome you to ask questions during the Q&A at the end of each session. Your contributions are invaluable, and we believe that diverse perspectives will lead to innovative solutions and a deeper understanding of the potential unleashed by intelligent robotics. Before we begin today's agenda, I would like to first welcome International Affairs Officer and Representative of ITRI Eindhoven, Yuliang Zhong, for a few words.
Thank you, Bingxiang, for this opportunity. Good morning, everyone. My name is Yuliang Zhong, International Affairs Officer and Representative of ITRI in Europe. I'm delighted to be part of today's event, as it will be an exciting opportunity to see you connected with MMSL's experts in robotic technologies and to be part of shaping the factories of future. ITRI is a world-leading applied research institute with more than 6,000 outstanding researchers. Our mission is to drive industrial development, create economic value, and enhance social well-being through R&D. We are dedicated to create new value and identify emerging demands for partners while facing global challenges and opportunities such as urbanization, aging societies, new productions and consumption patterns. climate change caused by global warming, and a post-COVID-19 era. ITRI has joined ITRI for decades and been selected as a chair this year. We have experience with aims of connecting the European innovative technology ecosystem and linking Taiwan with the world by providing a global technology collaboration platform. We facilitate longer and broader long-term partnership and bilateral and multilateral collaboration between Europe and Taiwan. We are looking forward to many connections that will be made with ITRI Europe office at the following today's event. Without further ado, let's begin with today's first section.
Thank you, Dr. Yang and Dr. Tong, for your warm welcome. For our next speaker, we've had to pre-record it since he is currently in Europe assisting a series of meetings, for the project that he will share about. And he will later join us live for the Q&A session. Now let's welcome Curtis to share on his experience working with the Horizon Europe project called Hard2.
Ladies and gentlemen, I'm Curtis Guan from Industrial Technology Research Institute. Today, it is my pleasure to be here to share my experiences with you. In this presentation, I want to describe how we joined the Horizon Europe project, Hard2, related to flexible manufacturing with advanced AI-enabled robotics. This is a Horizon Europe project. We call it Hard2. Hope you will get something during this presentation. Thank you. First, here is the outline of today's presentation. First, a brief overview of ITRI Robotics is introduced. Then, how we joined the Hard2 project, including the origin, the progress to Hard2, and what exactly Hard2 is. Finally, a conclusion is provided. As we know, ITRI was founded in 1973. It's an independent nonprofit innovation institution in Taiwan. And our scope is developing technology for commercializations and nurturing opening innovation with academia, industry, and global partners. That is why I am here to introduce our global collaborations, especially with the European partners. And the other scope is incubating and exploring startups for emerging industries. And as we know, the most famous spin-off companies are TSMC and the UMC in semiconductor areas. And ITRI has several offices around Taiwan and the global branches in Tokyo, Japan, San Jose, Silicon Valley in the United States, and Berlin for the European business. And here is our basic information about ITRI. We have Tainan campus and the headquarters in Hsinchu and the Taichung campus. And we got many staff with PhD degrees, master degrees, and we have total patents around 32,000 and more. And this slide will introduce our robotics achievement in the past years. And for the future, we have robotic development in ITRI. We have core technology related to controllers that we call it I Can Think. The vision system for robotic system that we call I Can See, and the several applications, use cases in the practical industrial area. We call it I Can Walk, and the mobility, I Can Move. And for the I Can Think, we especially developed the robotic controller and the navigation algorithm and the simulators with EasySync and ASASync. And the vision system is for the robotic system. We call it FOV vision, especially for object recognition and navigation. and I Can Walk, we have implemented several industrial applications, such as in aerospace manufacturing, drilling, or painting for the high-speed railway, and the grinding and the polish application for the semiconductor instrument, and the robotic weaving system for the composite material handling. And I Can Move, we have developed the dispatching system for multi-AMRs, and we have a fleet management software for AMR system. And this system right now is introduced to a semiconductor plant. Furthermore, we also have the medical robot is our focus as well, such as robotic bronchoscopy with diameter less than 3.5 millimeters. And here is our brief overview of our robotics achievement. Here, the next page, we want to say how we met Horizon Europe HARTU. And I want to introduce the origin of the origin. From 2002 and 2003, we have joined the European project, we call it Muffins. This project is related to the multimedia processing in the Impact 21 environment. Here we can say ITRI is one of the partners, and the other partners are Imperial College in the United Kingdom, and the IMEC for the Belgium, and the other partners from all over the European countries. And the other project from 2003 to 2005, and we got another partner from Switzerland. From this project before, based on our research capability in the past, almost 20 years ago, we joined these two projects. From these experiences with European partners such as Fraunhofer, Imperial College, IMEC, Vodafone, we have learned several lessons. The first one is the basic core concept idea is very critical. Use cases and the user scenario first. Then we, based on this user scenario and the requirement, we can implement the technology development. And diversity in the project partners. As we show, there are several various partners from the industries, including the universities, industrial company, and the academia research institution. So this diversity will bring the project different thinking logic and excellent sparkles during debate argument. And finally, we will get the consensus and the compromise from each other, and we will do our job or do our task, complete our task, what we have assigned, that we call it due diligence. And in these projects, they encourage participation in standardization activities and promote the achievement from the project to standardization organizations. So from these experiences, project achievement will be more applicable to the real and the practical use case in the industrial applications. That's why we have interested in joining the Horizon Europe project. So here is the slide showing our way to HARTU. In 2017, we, from the EU-Taiwan Industrial Policy Dialogue, we have decided we need to discuss on the AI robotics. EU and Taiwan agreed to focus on the development of AI plus robotics and start the preparation of robotics working group. And in 2019, we have established the EU-Taiwan Robotics Working Group. In this working group, we discuss the regulations, policies, and the joint research topics, especially on AI, data, and robotics. And this group is established based on the consensus of European Commission Director Generals. For example, DG Grow, DG RTD, and the DG Connect, especially for the ICT technologies. Through 2020 to 2022, both sides of EU and Taiwan discussed the joint research topics, including the digital twin, human-robot collaborations, and the AI robotics. And based on our consensus from both sides, in 2022, ITRI cooperated with the German AI Research Center, DFKI, and the Spain Research Institute, Technical, and the Philips Consumer Electronics, and the Turkey Automobile Company, forming a research consortium. We call it HATU. And this project got approval by European Commission, and the project kicked off in this year, January. And in this project, there is a company from Taiwan, INFA, also joined this research consortium. So, what exactly HATU is? HATU means is the abbreviation from handling with AI enhanced robotics technology for flexible manufacturing. And as we described in the previous slide, there are several partners from all over the Europe countries, and 2 partners, including ITRI and INFA from Taiwan. So all partners are listed as this figure shows. And what HATU is, we want to focus 5 use cases. The first one is the fixtures assembly, especially for the hand tool manufacturing. And here, this use case will be implemented by ITRI and the INFA, the Taiwan partners. And the second, the use case is the assembly for the consumer electronics. And this use case will be implemented by the Philips and the Technical. And this use case is from the Netherlands. And the logistics use case and the car assembly transport, this use case is implemented from Technical and the TOFAS, the Turkey automobile manufacturer. And especially for the packaging use case, is about the food handling. It's implemented by the Italian partners, Poliva. And in this use case, we want to focus on how to grasp a workpiece, such as how to grasp the workpiece in the right position and the right orientation. So here we will handle various workpieces such as hand tool, electronic components, foods and vegetables and others. And from grasping, we need to assemble all the components into one product. So we need to handle the contact force, assembly procedure, and the accuracy, and the compliance between the workpiece and the adaptation to various workpieces with different size and weight. And finally, we have to put or place the assembled product into the right place. So we need to handle the position and how to package all the workpiece. So here is our scope for the HATU project. And finally, here is a brief conclusion. From the slide before, HATU is a real international research project with 6 countries without mother tongue as English. So participation in this project, we will learn how to cooperate with various countries from Germany, Spain, Italy, Netherlands, Turkey, and Taiwan. We will, as we said before, we have to achieve the consensus and comprise to each other and do the assignment work with the due diligence. And here is the reference for the Horizon Europe Cooperation Framework. The European Commission has assigned 95 billion budget for the research and the innovation activities. And one more slide for the Horizon Europe. We have in this Horizon Europe, there will 49 European partnerships, including several clusters. For example, health, digital, industry and space, climate, energy and mobility, food, bioeconomy and agriculture. And for us, we will pay more attention on the AI and the robotics. So here is for your reference. If you are interested in participating EU project, we can cooperate. Thank you.
Hello, Curtis. Can you hear us?
Yes.
Hi, Curtis. Hi, so the audience just learned about your very unique experience working on the Hard2 project, and some have emailed us with some follow-up questions. So would you please be kind to answer them? Here I have the first question. How did the experience of participating in a European project inspire your research enthusiasm?
Yes, thank you for asking. So from my experience about how to cooperate with the European partners, we learn a lot of experience and lessons from during the project's execution, as we described in the slide. But the most important of all, or the most critical we have learned is we will conduct the research development from the real requirement from the real use cases or the real user scenarios. So from that experience, the main purpose of the technology development will inspired from how to make our life be better, or how to provide the better service. So that is why I have learned we need to develop such technologies to provide our human beings the better life or the better services. So here is my reply.
Thank you, Curtis. So there's another question. Could you give some words for those being interested in joining European research activities?
Yes, I think because, as I said, the first of all, the project will be inspired or will be erased from the will be issued from the real user requirement. So for those who are interested in joining the European research project, we need to keep our open-minded, and we have the motivation to want to bring the better life for our human beings, for our society, and even for our countries. So we need to be to have the curiosity about everything. So from the real use case requirement, we can use our knowledge to develop such technologies to support our goals and aiming it to the better daily life. So here is my advices for those people who want to join the European research project. Thank you.
Thank you, Curtis. Thank you for such a wise advice. Lastly, our audience would like to know, how can generative AI help technology development?
Yes, as we may know, the main purpose of the artificial intelligence, or we call it AI, the main purpose is AI can deal with the uncertainties that human may not aware. So during the whole manufacturing process or in our various applications, we may adopt AI to deal such uncertainties. And because the progress of artificial intelligence technologies is getting more smarter and more intelligent, so we can adopt AIs for different use cases and for various applications. So that we can adopt the advantage of the AI to deal several issues during our technology development. Thank you.
Okay, thank you, Curtis, for your recommendations. So I believe you have a full agenda ahead of you as you're in Europe right now. So these are the questions that we'll take for now. Thank you all so much for raising such great questions. And I hope that we can make many new connections after this. Thanks to you, Curtis, and have a good rest of your stay in Europe. And we look forward to hearing more about the new developments of Hard2. Okay, so our next speaker is Sergio. He will talk about robot vision system and Meta Factory. Sergio, please welcome.
Hi everyone, I'm Sergio. I am an engineer from the Robot Manufacturing Unit Department at ITRI. Today, I will talk about our intelligent robot vision systems and Meta Factory developments. I'm going to introduce to you two key products developed by our department, which are RobotTwin and FO Vision. Nowadays, in the context of global connectivity, an increased demand for efficiency and an accelerated production pipeline, businesses are making their physical factories to be described entirely in terms of software. No matter where users are located around the world, with the aim of 3D digital environments, virtual reality deployment, and a communication scheme between digital and real assets, users can perform sensitive operations in the digital world and bring optimizations to the real world. This is the idea for MetaFactory, which serves as a realistic virtual environment replicating actual factory layouts, robotic cells, and workpieces. Along with virtual reality interaction, real manufacturing sites can be completely software-defined. As a result, users can navigate all the way through the virtual scene and test sensitive operations safely. More specifically, RobotTwin, as part of MetaFactory, intends to link motion commands between real world and virtual scene. Users can deploy robot actions back and forth and collect relevant data from the real world to the virtual scene. The purpose of RobotTwin is to achieve paveable human-machine cooperation by connecting VR equipment combined with high-fidelity physical engine from NVIDIA Omniverse, resulting in a human-machine mixed interactive simulation technology. Here we have one video. For instance, the user is wearing a VR headset and also grabbing a virtual stick. Using one of the VR controllers, making the virtual world follow the stick. This action is related to robot teaching. In another case, we have a user wearing a VR headset. Meanwhile, the virtual robot is performing defined motion commands and compounds of data coming from the real world in the form of images, and other graphics are projected into the virtual environment for the user's interest. RobotTwin comes with two operation modes. The first one is known as follow target mode. In this mode, the user grabs the virtual stick and the virtual robot will follow this tool in real time. Therefore, joint states will be shared to the real robot, resulting in real-time synchronization. Robot safety is also considered as well, along with a virtual reset option to prevent both robots from any undesired displacement. One more feature here is that 3D animations of the workers are included in the virtual scene to make the virtual reality experience more realistic. Let us now refer to RobotTwin's second mode, known as play mode. In this mode, virtual robot is given defined motion commands. Those are shared to the real robot to achieve real-time synchronization. At some point, data from the real robot is collected and projected into the virtual robot. This is all part of a loop to simulate a running production line. So now, let us proceed with our second product known as FO Vision. FO Vision mainly consists of three pieces of hardware, which are a 3D camera, a particular lighting source, and an edge computing device. The system will collect light-controlled 2D images along with 3D point cloud data to be processed by an embedded AI object recognition model. At the same time, the system will compute pickable points over the workpieces, and it will command the robot arm with inverse kinematics to perform pick and place operations. As a matter of fact, AI training for object recognition demands reasonable training datasets. Therefore, manual labeling can be tedious and time-consuming. In contrast, FO Vision offers a modeling and automated AI tool capable of mapping real-world 2D images into their workplace 3D CAD model representation. This tool not only enhances the realism of the virtual environment, but also automates the generation of annotated datasets, capturing pickable and unpickable points for each workpiece. To ensure that valid training dataset acquisition is doable, the AI annotation tool makes use of our domain randomization approach. In this way, several parameters will vary, such as workpiece posture and quantity, camera lighting and posture, light intensity and color rendering as well. So here we can observe how the algorithm makes the change in the beam color, and also the objects are placed randomly, and they all have variations which will make the training dataset stronger. So with all this being said, let us observe FO Vision deployment. Considering a real working environment, FO Vision collects data from a container loaded with metallic pipes and commands an industrial robot arm. The synthetic training dataset generated to train the embedded AI object recognition model proves to be valid in this case. So here we observe the objects loaded into the container, and then we can see the masks obtained by the AI object recognition model. And all of this is the result of the trained dataset, which has the variations mentioned before. So this is all for my presentation, and I thank you for your attention.
Thank you, Sergio, for such an insightful presentation. Concerning your topic, we've also received some follow-up questions via email. So the first one is, how many configurations can FO Vision be deployed in?
Hi, thank you for the question. Let me reply right now. With the FO Vision, we handle two modes mainly. One is known as in-hand. This is well known in the field of robotics. And in this mode, the camera is mounted on the robot's end effector or gripper. And the goal of this method is to determine the transformation between the camera and the robot gripper or robot flange. And here we handle this case using checkerboard, and we have developed our methods to achieve this in-hand calibration. And we also consider the other mode called eye-to-hand. In this case, the camera is mounted apart from the robot, and we also make use of the checkerboard to achieve this calibration. As I mentioned before, we have developed our methods and algorithms to achieve this result. And honestly, we most of time use the FO Vision using the eye-to-hand mode, but we are open to consider other conditions. So we can work with different scenarios depending on the production line, and we have used the FO Vision pretty well recently. Yeah.
Okay, thank you so much for answering. Another question is directed toward the application of Robot Twin, the flexibility and possibility to integrate. Does Robot Twin accept other robots?
Oh, this is very interesting. Yeah, of course, we can integrate other robots into Robot Twin. For this, we have to get a file called URDF, which stands for Unified Robot Description Format. And with this file, we need to consider the robot links and joints and any other relevant information regarding dimensions or some configuration about the robot. As I said before, we have to consider if the robot used prismatic or rotational joints or a combination of both. Definitely we can make the integration with any kind of robot into Robot Twin, and we can also develop the communication between the virtual robot and the real robot. In this case, I was describing before universal robot case, and in this case we include real communication between the virtual UR10 and the real UR10 through TCP/IP communication, and this is possible to do with any other robots depending on the API of the specific robot. So definitely we can consider more robots, and as I said before, we have to go with the URDF file, and I also need to mention we have to collect the CAD model of the robot, and this file must be with the real units. I mean, with respect to the real robot.
Mm-hmm.
Yeah.
Okay, thank you for such a comprehensive answer. What about if the user wants to use Robot Twin and VR? What are the specifications required in order to adopt this configuration?
Oh, yes, sure. During my presentation, I mentioned that we have developed Robot Twin based on NVIDIA Omniverse, and because of this, NVIDIA has recommended some hardware. For instance, you have to, if you want to make a good setup to load VR functionality, you need to consider a CPU consisting on the Intel Core i7, at least the 9th generation, or you can also go with AMD Ryzen 7 with 8 cores at least, and you have to consider 64 gigabyte of RAM memory and the storage at least maybe 500 gigabyte. And in terms of GPU, you have to go with maybe RTX 30 series at least. And well, virtual RAM, the GPU should go with 10 gigabyte. Yeah, this is the recommended configuration from NVIDIA Omniverse to make use of Robot Twin. And yeah, I believe it's quite correct. Yeah.
Okay, thank you for your recommendations. And lastly, we have another question. What is OpenUSD, the format behind digital scenes?
Oh, this is pretty interesting. This OpenUSD was developed by well-known animation studios in the world and intends to bring several configurations regarding 3D CAD file workflow, and it's well known in the industry that right now there are several sources to process the CAD files and 3D modeling objects. There is like paid software and open source software, but the OpenUSD brings all of these together, and it has several advantages. For example, it's highly interpolar. It has it's possible to bring different files all together, and it can manage several layers in CAD files. So this allows digital works to work, and it is also possible to collaborate remotely with this platform. You can bring several workflows into one, and I really believe this is a very powerful piece of software which we can understand pretty well, and we use this as part of our development.
Okay, thank you, Sergio, for such a comprehensive sharing. So I think that's about how many questions we can take for now. However, you can continue to drop your questions in the chat function, and we will get back to you after the event. So thank you very much, Sergio. Now let's invite our third and last speaker of the day, Josue, to share on autonomous mobile robots, or AMR. Welcome,
Hello, everyone.
Josue.
My name is Josue. I'm the Deputy Technical Manager of the Service Robots Department, and today I'm going to give you a short presentation about the autonomous mobile robots that we have developed in our department. So my presentation is going to consist of two parts. First, I'm going to give you a short presentation of the intelligent AMR solutions that we have developed. And then in the second part, I'm going to show you some interesting applications where we combine robotics with arts. In our department, we have been developing autonomous mobile robots for quite some time, but we also have developed other type of robotic systems. For example, we develop a human-like robotic hand, and regarding the autonomous mobile robots, we have developed some mobile-based robots, and in this case, this mobile-based robot can carry 100 kilograms, but we have developed platforms for 250 kilograms, and we are hoping to develop soon platforms for up to 2 tons. And we also develop mobile arm robotic systems, like, for example, this robot here called Mars Lite. Now, in our intelligent AMR solutions, we need to integrate mobility, navigation, perception, manipulation in the case of mobile armed robots, and also human-machine interfaces to use these robots. And using all this integration, we can develop solutions for the industry. For example, the mobile arm robot here that we can use for pick-and-place applications, and other applications that requires the robot arm. We also have developed some applications for the autonomous forklift. For example, in this case, we developed a technology to perform the pick-and-place of a pallet. And we also have done some outdoors mobile robots where we use a robot to monitor an outdoors area for some companies. And in the case of service, we have also been developing technologies to be used in convenience store, hospital disinfection, and lobby cleaning. Now, for the case of the industrial applications, I'm going to give you the two short study cases. And the first one is the pick and place in a manufacturing cell. And as you can see in this video, this holonomic mobile manipulator is picking a workpiece from this manufacturing cell, and then it will place it in other locations around this manufacturing cell. This was done to mimic a real manufacturing cell where we have multiple processes that these workpieces have to go through, and this mobile manipulator will be in charge of moving around these workpieces. We also use the same mobile manipulator to perform other specific tasks. For example, here we have the LCD carrier polishing, where we use the mobile manipulator to approach this LCD carrier, and then we perform the polishing in 4 steps. And as you can see in this video, we're polishing the first quarter of this LCD carrier, and then the robot will move to the next, to the 3 other locations where we will perform the polishing task. For these industrial applications, we developed the following technologies. First, we develop a task manager and a task executor. The task manager will take the task one by one, and it will use the task executor to execute this task. And combining these technologies, we can do quick reprogramming of the robot. For example, we can change the arm trajectories, the mobile-based goal, docking operations, and other tasks. And this task definition uses a simple and intuitive XML format. So this is really easy to reprogram these robots using this task manager and task executor. And this task executor can also use relative reference frames. For example, in the 2 videos that I show you, we use April tags to reference how the movements are going to be done. And these 2 technologies are also easily adaptable to a dispatching system or a manufacturing and execution system using a task server, which leverages the task manager. Now, in the case of the service applications, we have the lobby cleaning, as you can see in the top left. This is an Ackerman type robot, and we use this cleaning robot. We adapt our technology to this existing cleaning robot to perform lobby cleaning. And in this case, you can see the robot is performing this cleaning trajectory that we computed based on the cleaning area that the user wants to do. We also have the hospital disinfection, which uses a similar technology where we can select the areas that we want the robot to clean, and then we can also select the areas that the robot should not go to. And this was already applied in the National Taiwan University Hospital here in Taiwan. The technologies that we developed for these 2 service applications was a multi-area, multi-block cleaning path generation, which this means that if you have a big map and you want to clean multiple areas, you can select these multiple areas one by one, and also select some blocks that you want this robot to go to. And then the robot will find the optimal path to move between these 2 areas. And we can also select the forbidden areas, which are the areas that we don't want the robot to go, maybe because we're doing some maintenance there or for any other reason. And we also develop an intuitive operation, which is an Android-based HMI, as you saw in the lobby cleaning case, where we have the screen to select the map that we want to use for this cleaning, or to select the task schedule or other tasks. And this selection of the allowed and forbidden areas can also be done through this HMI. And we can also generate the task schedule for all the tasks using the HMI. Now, we also have been doing some research to execute complex trajectories with mobile manipulators. And as you can see here in the top left, the robot is moving around this Lysagius path, and it's continuously tracking this trajectory while it moves. You can also see on this second example that the robot is following a sinusoidal path. Now, this type of trajectories can be used for certain applications where you actually want the mobile base and the robot arm to move continuously. A simple example is if you want to open a door, you might need to do this. You can do this step by step, first moving the platform and then moving the arm. But a more optimal way to do it is by coordinating the movement of both the arm and the platform to open the door. And the technologies that we develop in this case is the coordination of the robot arm, and in this case was a non-holonomic mobile base, but we can adapt for holonomic and non-holonomic. Just the non-holonomic case is more challenging, so that's why we work on it. We also had to do the redundancy resolution to execute these complex trajectories because this is a 10 degrees robot, 10 degree of freedom robot arm. And because this is a highly redundant robot, we also need to consider the singularity avoidance to allow the robot to perform this task. We also included a self-collision and joint limit avoidance as constraints to execute all these paths. So in both videos, what you saw was the robot executing this task and continuously avoid the singularity and also continuously avoiding self-collisions and joint limits. Now, in the second part, as I say, we're going to show you some examples of how we combine robotics with arts. And in the first case study, we have the three-person project by the artist Taoya Lueng. And this project was presented in the Patch Lab Digital Art Festival last year in Krakow, Poland. And in this case, what the artist requested from us is he wanted to use a VR headset that you can see on the top left video. And the headset is at the beginning showing a video that is the idea of this artist to show around the area where he's trapped right now, where he feels he's trapped because he can only see around. And then after this video finishes, we will see that the mobile manipulator on the top and the bottom left will start moving and tracking the movements of the headset. So what the artist requested is, can we follow the movements of the headset around this area? So he will walk around this area, as you will see in a couple of seconds. So as you will see here, once the video finishes on the top right corner, the mobile arm robot will start moving. And what you see right now on the top right is the stream of the camera mounted on the end effector of the robot arm. So right now, as the user is, in this case is the artist testing our project, is moving around this area, the mobile arm robot will follow his movements. So it will follow the movements of the head as well as his location around this area. And as you can see, on the stream, we're constantly streaming all the movements so that the user feels like it's actually in Taiwan. And this was recorded in a theater in Taipei, while, as I say, the user is in Poland, in another country. Now, for this specific case, we needed to develop an arm target follower. As you can see in this video, the arm is following the movements of the headset as the user moves around. And we also needed to develop a mobile-based target follower. And in this case, the mobile base needs to follow a target. And the arrow here is pointing to the direction that we have our target right now. And while it does so, we also have to consider there might be some obstacles around the environment, so it needs to avoid moving to those areas. Now, the technologies that we developed for this project was a remote control for the mobile arm robot. And as I told you, this is a remote control from a different country to Taiwan. And then we developed a smooth Cartesian velocity control for the 6 degrees of freedom robot arm, as you saw here with the movements of the arm. And this target follower also need to consider the constraints like joint limits and the workspace limitations. And for the mobile-based target follower, we included the collision detection, as I just mentioned. And all the execution that we performed was using the MQTT protocol. So this is how we receive the task from the headset to tell us where the mobile manipulator should go. Now, the second study case, we have this artist ask us to perform the movement of a mobile platform in this circular trajectory that you're seeing in this video. In this case, the robot must just move around this circular trajectory constantly while a performer is moving around it. And the challenges in this project were that first, that the lighting conditions change a lot. So we have really dark areas when the performer is moving around, and we also have really a lot of light in some areas. And this, as you can see here, the mobile base is already moving around this circle. And the problem was that because there's going to be, the audience is going to be seated around the performance area, there is no way to acquire features to actually localize the robot inside this circle. So the challenge was how we can actually develop some localization algorithm for the mobile platform so that it can move around accurately inside the circle. And as you can see here, the performance as it is moving around the circle, and we're showing some video through this transparent screen, the robot will keep moving around the circles with high precision. Now for this specific case, we develop an indoor localization system that is robust to illumination changes. And we also develop a precise trajectory tracker for this mobile base. This is the end of my presentation. Thank you.
Thanks, Josue, for such an informative presentation. We have also received beforehand some questions concerning your topic. So the first one is, how do your robots communicate with the dispatching system, or MES?
Thanks for the question. So as I mentioned in my presentation, the robot has what we call a task server, and this task server can be easily adapted to a different format that is used by the dispatch system or the MES system. So we can actually just write a couple of lines just to convert the format from the MES or the dispatch system to a format that actually our task server can understand, and then in this way we can execute the tasks.
Okay, thank you. Another question is, what kind of data and how did you send this data over the internet to the robot to follow the user's movement in the free person project? And also, can you use the same data and follower algorithms with other robots?
So for this project, because we were capturing the data from the headset, what we did was trying to capture the position and orientation of the headset after we perform a simple calibration. This calibration was done when the user wear the headset for the first time. We will save this data to use it as a reference for the rest of the performance. And then we will take this data and use the MQTT protocol, as I say in my presentation. And when the robot receives this data, it will filter it out so that we actually have a smooth movement and the user does not feel like weird movements because of the vibrations. And our algorithms, both follower algorithms, were developed to be used with any other robot. So yeah, we can use the same data or other data and still use these follower algorithms for other applications.
Okay, thank you. Another question is, what type of indoor localization technology did you use that is robust to the large illumination changes?
So, like I said, for this project, the main issue that we had is we could not use a LiDAR technology to do the localization. Because the performance was done in a theater, we needed to find other ways to create this localization system. So what we did was install a couple of LED lights on top of the screen that was on top of the robot, and they form a special pattern. And by using two cameras mounted on the ceiling of the theater, and using some estimation algorithms that detect this specific pattern, and we also calibrated the cameras to actually just detect this specific infrared light. We will try to estimate the position and orientation of the robot inside the performance area. And then using this information, we could perform the trajectory that we show in the video.
Okay, thank you. Another question is directed to a different field, to smart farming. What is your perspective of autonomous robots in this field?
So there has been a lot of development of autonomous robots in the smart farming. We are also currently working in one of these projects. And I think the main problem that we are facing is how to cost down this type of systems, because especially for the localization equipment that we need, and because we're going to use it outdoors, I believe that we need to find ways to cost down this kind of equipment, or try to find innovative ways to perform the localization so that the farmers feel more motivated to use this type of robots in their farms. Because while the prices are a little bit expensive, I think it will be really complicated to have them use these robots.
Okay. Thank you, Josue. I think that's all the questions we have for today. And so we look forward to the potential collaborations we will have with AMR technology following today's exchange. So thank you, Josue. So ladies and gentlemen, this concludes our event today. But before we all sign off, let's invite Dr. Bingxiang Yang back for some closing remarks.
As we conclude today's event, I thank you for being a part of this deeply insightful and enlightening online forum. Our collective passion for innovation and dedication to shaping the future of manufacturing have made this an exceptional exchange. Through the experience of insights shared by our researchers and the thought-provoking questions raised by our enthusiastic audience, we have delved into the transformative power of intelligent robotics in driving the evolution of smart factories. We have witnessed how these cutting-edge technologies are revolutionizing production processes, enhancing efficiency, and ultimately paving the way for a more sustainable and competitive industrial landscape. Let us forum serve as a stepping stone towards forging new partnerships, fostering innovation, and nurturing the growth of intelligent robotics in the manufacturing sector. I encourage you to stay connected, continue to exchange ideas, and explore possibilities to collaborate. Once again, thank you all for the active participation, and I look forward to meeting you again in the future endeavors as we collectively shape the path to smarter and more prosperous factories.
Thank you, Dr. Yang. Indeed, we look forward to staying connected with our audience and for future collaborations. For those who haven't had the chance to share your feedback, we'll leave the QR code on for a few minutes after the event. And we've also shared this link and an email in the chat, so you may write us with follow-up questions that we didn't get a chance to answer today. Thank you all, and let's stay connected.